Hi, I'm Spencer Hancock, and I'm the lead for Group 2, and we're doing the commercial air conditioning unit, as we've all seen. So first of all, we're going to get off with the safety. So, obviously you want your proper equipment worn at all times, long pants, proper shoes. Important right here is do not touch any of the components, as they can get pretty hot, possibly. Don't turn on the heater unless the fan is running, and if you do this, you might burn up the heater. And also, there's a fire hazard, so make sure you know where the fire extinguisher is. So the objective of this lab is we want to understand the efficiency of the air handling unit. We're going to want to understand all the physical components of the air conditioning, and we also want to understand all the variables that are in these equations that we're going to be working with. So first thing is understanding the air handling unit. So here's a simplified diagram of what we're going to be working with. So as you can see, first, air is going to be entering, and typically it's relatively warmer than the rest of the air. And what it does is it passes over these cooling coils right here, which sort of acts as like a heat exchanger, which will colder than the air coming in. So it'll take the heat from it to this T leaving right here, in which this T leaving is blown into the air conditioning through this fan right here. And because the fan's adding a little more energy, the air that's leaving the fan is going to be typically a little bit warmer than the air that's leaving the cooling coils. So next thing we have is our efficiencies. First kind of efficiency we have is this coil bypass factor. And so what this measures is it measures the percentage of air that doesn't get conditioned as it passes over the cooling coil. So like this little heat exchanger. So to calculate this, you can take the dry bulb temperature of the air leaving, subtract it from the cooling coil temperature, and divide that by the temperature of the air entering, and might subtract that from the cooling coil. So there we get some kind of efficiency. Our next kind of efficiency is the energy efficiency rating and the coefficient of performance. These are similar in the fact that the coefficient of performance pretty much just kind of converts this electrical input to BTUs per hour. And what this pretty much says is it's comparing the cooling, how much this AC can cool compared to how much power it can take. Here's our apparatus. So what we have is first is the cooling loop. So here it starts with the AC unit. So it operates with already conditioned air from the AC unit. Supply air fan pushes it up to the supply air heater. So this right here can change the temperature of the air to whatever is desired to be entered into these two rooms that are controlled by the valve boxes right here. And you can see it diverges into these valve boxes, which operate as dampers, which can control the flow of air to monitor the temperature of the air in the room, so whatever you want it to be. So then we have this other little loop that's analogous to the cooling loop. It's the heating loop. Unlike the cooling loop, which is an open loop, the heating loop is a closed loop, so air is going to be running through here a good bit. And so it increases quickly since it's not open to the ambient. And then so this hot loop fan will send the air into this hot plenum thing, and then they'll be separated by two chambers. So here's these two chambers that's the hot plenum is in between. So we have chamber A on the left and chamber B on the right over here, and the hot plenum runs in between it on the, yeah, you can see it there. So chamber A shares the wall with the hot plenum, which is, you can kind of see it running down there. And so its thermal resistance to the hot plenum is, it's got the outside surface, it's got a sheet metal in there, and it's got the internal surface. Chamber B doesn't share the wall with the hot plenum. So it's got the internal surface, I'm starting from the bottom here, internal surface, sheet metal little thing, the air gap between it, outside surface. You can pretty much see all that. So the procedure we have here, it's pretty complicated, so I'll try to simplify it up a little bit. So the first thing you want to do is you're going to start your program. You're going to record the dry bulb temperatures of the room and the relative humidity. You can kind of read along here. So from valve 1 and valve 2 separately, you're going to force the damper open, which will open up those valve box dampers. Then you force it closed. So in the cooling loop, then you're going to come and do something with your discharge air drivable temperature. So pretty much this is just setting up all your stuff. It's pretty detailed, but we can follow along in the handouts. Back to the cooling loop. Yeah, so you want to make sure you wait 2 to 3 minutes before recording all the data that you just set up in that really detailed section. And then you're going to record measurements every 20 seconds for chamber A, the temperature and the volume flow rate, and chamber B, temperature and volume flow rate. Go on for 30 minutes and make sure you shut it down in this order: the heaters, the fans, and then the AC unit. Sample calculations here, I got the heat rate, which is the temperature times the area times the thermal resistance, divided by the area to get the heat rate per area. So you can see the thermal resistance for A, a little bit lower than B, so obviously it's going to have a higher heat rate in there. And then here's your volumetric flow rate, which is the heat rate divided by the density times the specific heat times the change in temperature. And obviously, since the heat rate was a little bit higher for chamber A, it's going to need a little bit more air in there than B. Any questions?
So what is controlling the opening and closing of the VAV box?
It's like a mechanical damper, so it'd be like a valve. It'll open and close.
So why will it open and close?
Why? To control, it can control the volume of air that flows in there. Right?
No, I want to know what is telling the VAV to open or close?
Like, what's making the valve open and close? I mean, I guess it would be some kind of sensor or something, like a computer system.
What is it sensing?
What is it sensing? The temperature of the room?
Yes.
Okay.
So, do you know how the temperature is measured? So you have the box, right? Go to the box.
This?
The box.
This?
Yeah. So how many sensors you think are needed to? You saw the box in the lab last time, right?
No.
You haven't seen the apparatus? It's a pretty big box. How many sensors do you think are needed?
I don't know. Maybe like 3, maybe? Like 3 or 4?
Is it enough to have a single sensor for a box like that?
No.